Hi y'all, we're going to go ahead and start chapter 3 today. Chapter 3 is only going to have 2 videos because I took some of it out and put it into chapter 2. So this is a little bit shorter of a chapter, which is good. So we're going to start talking about the periodic table, and we're going to learn some properties about the periodic table and just the locations of the different groups and types of elements, things like that. I do strongly suggest that at this point you have a printed periodic table. Can you continue to use the online one? Absolutely, but it's going to be better for you to write on a physical periodic table. If we were in a class setting, like in person, I would have printed ones for you that you would write on. Okay, but some common things about the periodic table. The periodic table is really a compiled list of elements that has these recurring patterns of both physical and chemical properties. And that's what periodic means. It just means a repeating pattern. And so here are some patterns in boron's group, which is element number 5. Okay, so as you notice, as you go down the column, radius increases, but really so does density. And we'll talk about that later on in this chapter, so the next video, but they all have patterns that kind of match that. So just some history on the periodic table. It was in the 1900s, sorry, not the 1900s, the 1800s, that scientists really noticed that, hey, these properties are similar and we can arrange them in specific ways. So Mendeleev, it is very important that you know his name. He is considered the father of the periodic table, and it's because he summarized his observations and kind of put it in a fluid table. And he said that when elements increase in order of mass, certain properties reoccur periodically. And because of that, he actually left blanks in his periodic table, and he was able to predict their properties of undiscovered elements at the time. So he was able to predict gallium and also germanium, and it came to pass that he was correct. His predictions were very spot on, as you can see in the table at the bottom. So because of that, that's why he's considered the father of the periodic table. We now do not list elements in order of increasing mass, but increasing atomic number. Mass kind of falls in line, but some of them are a little off from just increasing mass. I do want you to note rows go across. Okay, and then columns are the ones that go up and down. Okay, so rows are normally called periods, and the way to remember that rows go across are that, like the row, row, row your boat song, you have to row across a lake. Okay, columns, the way to remember that those are the ones that go up and down. Columns hold up buildings, and if you think about the old Roman buildings where they had lots of columns, or even like plantation homes that had columns, those hold up buildings, they go vertically. Columns are called groups or families. Either one of them is fine, but you do need to know that they both are used for columns. Also, if you are in the same group or family, you're going to have similar properties. And the way it's sometimes easy to remember this is that you probably have similarities to your family members, like your brothers or sisters or parents. And so, like for me, I cannot really deny any of my siblings or even my daughter who looks just like me because of all of our physical similarities. So it's the same in elements families. So we're going to talk about the metals, the nonmetals, and the metalloids. But first, we're going to talk about the main group elements. And the main group elements have a letter A at the top. And really, it's columns 1 through 2, and then 13 through 18, just depending on what periodic table you're using. Also, they're 1A, 2A, 3A, all the way up to 8A. Okay, these specifically are very predictable, which is why they're main group elements. The transition elements, or the inner transition elements, that's the D and F block. And this is S and P. Those do not have as predictable properties. They're much less predictable, and so they don't fall in line as easily. Also, sometimes those intertransition and transition metals, they have a B over them in their column. So here's just an example. So we've got the 1 through 18 on the columns, but then we also have these A's and B's. If you remember in the last video I talked about, those really give us a rough estimate of valence electrons. And again, the transition elements, they don't always fall in line with that, but they follow some pattern, just not as well as the others. Okay, Coulomb's law is going to appear here. Really, we're going to deal with Coulomb's law in the conceptual sense. We're, of course, not going to calculate, and really all of this is a constant. Sometimes we just say that this is K for some constant because all of those values are constant. But Coulomb's law describes the attraction and repulsion between those particles. So Q1 and Q2, these are our charges for our particles, and then, of course, radius is R. The reason we bring up Coulomb's law is for this effective nuclear charge, which is really what's most important, is this bottom bullet point. So the effective nuclear charge is the amount of attraction the electrons feel from the protons. And most of the time when I write it, I do go ahead and write ZEF. That's just the abbreviation. Remember, Z is the symbol for protons or atomic number, and then it's just the effective charge on that nucleus. So transition metals and intertransition metals, again, they exhibit those differing traits from main group elements. Just remember that they are not predictable. So here's some things that are not predictable. Notice chromium has an expected electron configuration, but then when you do it experimentally, that's not the same electron configuration. The reason is because the electrons are trying to get in their most stable configuration, where they're following as many of the rules as possible, the Hund's rule, Pauli exclusion, and Aufbau. And by moving each other around, they're becoming more stable in their orbitals. Now, I will only ever ask you the expected electron configuration, not experimental. So here we're just seeing that the different columns in that specific column or family, they're going to have similar electron configurations. And if you notice that N piece is always the same. Notice here we've got 2s2, 3s2, 4s2. So everything in the alkaline earth metal column is going to end in s2. Same thing with the halogens, p5, p5, p5. Okay, so they've got these same properties in their families. So the noble gases are the first family that we're going to talk about. That is the farthest column to the right. They're all going to have 8 valence electrons, except helium. Helium only's got 2 electrons. Because of that, they're non-reactive or inert, which just means that they don't react. And that's because they're stable. They've got that full outer shell on a Bohr model. Okay, so there's no really electron movement happening because they're full. And that's why they're non-reactive. Also, while we're here, these would have 0 charge because there's no electrons moving. The next groups we're going to talk about are the alkali metals. The alkali metals are the very first column with hydrogen, except hydrogen is not a metal. So hydrogen is not included for the alkali metals. Okay, they will have 1 more electron than the noble gases, and they're going to be in that first column. And they will lose that electron to form this cation charge of +1. Alkaline earth metals, which is the next column to the right, they have 2 more electrons than the noble gases. And so in their reactions, they're going to lose 2 electrons, again forming a cation of a +2 charge. Just remember that cations are going to lose electrons, while anions are going to gain them. Those transition and intertransition metals, just remember they're in the D and F block. and they're going to lose electrons, but they lose them first from S. Then they pull D ones when they lose them. Okay. And here's an image showing the metals, the metalloids, and the nonmetals. I do need you to make sure you know which are which because these are easy test questions that you should not be missing. Okay, you need to make sure you either have it labeled or you even have this slide pulled up if you don't know which ones are which. That way, if asked, you could identify, yeah, nickel's a metal. Yeah, arsenic is a metalloid. Things like that. I do want to talk about real quick. It's pretty common that I ask where the metals are on the periodic table, and some people put the middle. Well, here's the middle of the periodic table. And yes, there are metals there, but really from here over, those are the metals. So it's really most of the periodic table and to the left. Metalloids, those are the ones that are on the stair steps and they're touching that zigzag line. It is all of them touching that line except aluminum. Aluminum is a true metal. And metalloids will exhibit behavior of both metals and nonmetals, so they will either gain or lose electrons depending on what side of that stair step they're on. If you're wondering what stair step I'm referring to, this dark black line on this image, that's the stair steps I'm referring to. Nonmetals, those are to the right of the metalloids. They're going to gain electrons. And remember, nonmetals are going to form anions because they're gaining those electrons. Halogens are the first nonmetal group we're going to talk about besides the noble gases. Really, this is the only other named group we're going to discuss. They are all nonmetals. They will have one less electron than a noble gas. So what's going to happen to them is when they're in a reaction, they're going to try to gain that extra electron. And when they do that, they form anions of a -1 charge. So again, metals will always form cations when they're in a reaction. And that's because they're going to lose their extra electrons. They will become positively charged. Nonmetals in a reaction are going to form those anions because they're going to gain electrons. Here are some common charges. These are predictable ones. I do suggest on your periodic table, you go ahead and write these in on the top of each column. Okay, notice all of the ones in the center, those have differing charges, those transition metals, so they don't have charges over them. But notice column 4A, that's carbon's column, it has plus or minus, and that's because it's pretty split of whether they're going to gain or lose their electrons. Again, always remember that regardless of what column they're in, so like next to tellurium is antimony, and antimony would normally gain them because of the metal properties. It's more metallic than not. So it'll be positive instead of negative. Things like that. Okay, so predict the charges. So we go to aluminum. It's under boron. So aluminum would be 3+, and sulfur would be 2-. While we're here, I do want to go ahead and write their electron configurations of ions, just so you know. Okay, so aluminum is going to lose 3 electrons. So I'm going to do normal aluminum. Okay, and remember, they're going to lose those valence electrons first because they're on the outside. So when it loses 3, it's losing these last 3. So aluminum, after it's become a cation, is going to look like neon. Okay, because it lost all 3. Sulfur is going to gain 2 more. So sulfur will look like argon. 1s2, 2s2, 2p6, 3s2. And instead of being 3p4, it gained 2 extra ones. So it's going to look like 3p6. Okay, now it wants us to do nitrogen's charge. Nitrogen will also be 3 minus. And rubidium, so this is for nitrogen. And Rb is just going to be +1. Normally we just write plus for that, or minus for the halogens. All the other ones you are going to have to write a number for. And that is it for today. So I hope y'all had a good lesson. If you need any help, please let me know.